to share your presentation. You can start whenever you want.
Thank you, Andrea. Thank you, Andrea, for the introduction. So let me figure out how I'm gonna share this, because, okay, now I think I can share it. Let me know if you can see my screen. It's loading. Okay. So I hope that you can see my screen. Is that correct?
Yeah, I can see.
Perfect. All right, so let's get started. So first I'm going to talk about, as Andrea said, first I'm going to talk about Ludwig, and then briefly I'm going to touch upon one project that we did using Ludwig called COTA for customer support. So let's start with Ludwig first. What is it? It's a deep learning experimentation toolbox. It's based on TensorFlow, and the main selling point is that it doesn't require code for you to write in order to obtain a deep learning model and to use it for obtaining predictions. It has been released about a year ago, a little bit more than a year ago. It's been pretty successful on GitHub. Many people download it. There's a lot of commits a month and also more than 60 contributors. So it's been pretty nicely adopted so far. And this is a set of companies and universities that use it either in their production setting or they use it as a teaching tool. All right, so the main principles behind the Ludwig is that, first of all, I wanted to make a tool that was general. And so it's based on a new abstraction that is based on data types that I'm going to dive into in a minute. And that allows to cover many different deep learning tasks. It's also flexible because I wanted to make a tool that was useful to both the novice user that doesn't know how to write a deep learning model, but also to the expert user that may know all the details and all the nuts and bolts, and they can still use Ludwig for facilitating their own process. It's extensible so that whenever there's a new model, a new feature extraction, anything new that comes up, it's really easy to add it to Ludwig. I also included some, more than 20 actually, visualizations in order to make at least the predictions and the performance of your model kind of understandable. It also has a programmatic interface that makes it really easy to use if you're a programmer, and it's also open source. Let's start with a simple example. Let's assume that you have data in this format where you have like a table with two columns. One is news and contains some text for the news, and the other one is class, and it's like the class associated with that news. And the goal is to train a model that, given a new news, predicts the class. In Ludwig, what you have to do is you have to just run this command, Ludwig experiment. Data CSV here is like a way to specify where the data lives, and model definition is, in this case, just a string. This is YAML, and it contains, it's a dictionary with two values, input features and output features. Both of them are lists with only one element in this case, because we have only one input feature and only one output feature. The input feature has name news, because the name has to be exactly the name of the column of your data, and type text. And the output feature has name class and type category. This is all you have to specify in order to train a model. If your model definition becomes longer than this, you can save it into a YAML file and then provide the path to that file. What happens is that Ludwig will take the data, split it in training, validation, and test, but also you can provide already splitted data if you want. We'll train the model on the training set, validating on the validation set for early stopping, and in the end, we'll predict on the prediction set, on the test set to obtain evaluation of performance of the model. This is what you will see in the command line after the first epoch. You see there's a set of metrics, in this case, the loss accuracy, and it's a K for training, validation, and test set. After a few epochs, the validation on accuracy increases, which is what we want. And then it plateaus, and so after a certain amount of epochs, in this case 10 epochs, the training will stop. And the best model on the validation set will be used to obtain predictions on the test set, and metrics on the test set will be reported, like all these metrics that are like overall metrics, but also per class based metrics. So you have all these detailed metrics that you can analyze if you want to figure out how well your model is doing. So this is basically Ludwig in a nutshell. But now I'm going to show you that you can do much more with it, and I'm going to also explain how it does it work. At training time, what happens is that you provide your raw data, and there's a preprocessing step that creates some mappings. For instance, a mapping from strings to integers for the class type, for the category type. And these mappings are going to be used later on for prediction too, and maps the data into tensors. These tensors are provided to the model training component that saves weights and upper parameters. At prediction time, you have some new data, and you map it exactly in the same way you mapped the training data using the mapping that you saved before to obtain tensors that are provided to a model prediction component that loads the model from the weights and the upper parameters that were saved previously. And the prediction obtained by, and the scores obtained by the model are then mapped back into data space through, again, the same mappings. And in the end, you have your final predictions. When you run experiment, which is the command that I showed you, what actually happens is that Ludwig first runs training and then runs predictions. So what you save are the weights, the upper parameters, and the mappings. But at the same time, what is produced by the model is the final predictions, but also some training statistics and some test statistics. All these files can be provided to the visualization component in order to obtain some graphs and visualizations. Then I'm going to show you some examples at the end. So what happens under the hood? What you have is that the main selling points and the main magic happens in, first of all, the data type abstraction that allows to cover many different use cases, as we're going to see in a minute. But also the fact that you just declare in a YAML file whatever you want to predict rather than the implementation of how you want to predict. And finally, if you're familiar with Python, there's a heavy use of KV-args, which allows for the same parameters that are available in the model definition to be used in the code directly, so you have full control of the code. If we go back to our example, this is the part of the model definition. This overrides some defaults and becomes this bigger thing that seems big and scary, but it is not. I'm going to explain to you what it does. It's divided in 5 different sections, and 2 of the sections are input features and output features, of which we have seen an example. But there's also a combiner component that I'm going to explain in a second. There's also a training and pre-processing part to the model definition so that you can specify training parameters and pre-processing parameters easily. So why do you need this input combiner output structure? The reason is that Ludwig supports many different data types, and you can specify multiple data types at a time. So for instance, it supports text, category, numerical, binary, sequence, vector, set, bag, image, time series, audio, H3, which is a geospatial way of describing your data, and date. And it can predict for most of them already. We'll complete the list of the ones that can be used for predicting. And when you have more than one input, what happens is that your data is first encoded, and then you have the encoded data, which is basically a vector, and has to be combined. Multiple of those has to be combined in one single representation, and then can be used for obtaining predictions. And the power of this architecture is that depending on the specific instance, you can obtain many different machine learning models. For instance, if you have text as input and category as output, which is the example that we've seen at the beginning, you obtain a text classifier. But if you have image as input and text as output, you can have an image captioning system. If you have category, numerical and binary as input and numerical as output, then you have a regression model. If you have audio or speech as input and binary as output, then you have a speaker verification system. If you have text and image as input and binary as output, then you have, for instance, a visual question answering system. Moreover, each input type has a bunch of encoders associated with it, and each output type can have multiple decoders. And this allows for swapping in and out different models. For instance, for text input, I have these 6 different options at the moment, which are text CNN, parallel CNN, text parallel CNN, RNN, CNN RNN, and a transformer. And you can choose which one to use by just specifying the keyword encoder in your model definition. For instance, if you want to use a parallel CNN, you have to specify, well, the name of the column, as I explained at the beginning, and also the type, which is text. But you just have to specify encoder and which encoder do you want. And in this case, it's something specific to text. You can specify the level if you want to encode at a word level or a character level. And then you have all these gray parameters that are the defaults and are all optional. But you can change them if you want. in order to customize your model. So for instance, you can decide how big are the filters, how many filters to use, how many fully connected layers, how big they are, and so on. And when I was telling you about KVArgs, this is like the signature of the init function of the class that implements the parallel CNN, and you can see that the parameters are exactly the same. But if you want to have a stacked CNN, all you have to do is to change the encoder to stacked CNN, and you have all the parameters for the stacked CNN, the same for the stacked parallel CNN, and for the RNN. As you can see here, the parameters are pretty different. You have, the cell type, which would be GRU, LSTM, etc., the state size, etc., and if bidirectional or not, and so on and so on. So you have full control. And the same is true for the CNN LN. This structure actually allows for a lot of code reuse, and the same encoders, for instance, can be used for also sequences, time series, and audio and speech encoding. For images, I have only 2 encoders at the moment. I welcome contributions if you have more. The stacked CNN is similar to VGG, and the ResNet is close to state-of-the-art. For numerical and binary features, the encoding is really simple. Numerical features is just a single fully connected layer with normalization just for the sake of rescaling. And for binary features, they're just casted to floats. Category features are encoded with either dense embeddings followed by fully connected layers, or by one-hot encodings followed by fully connected layers. It's your choice. Sets and bags are similar to categories. The only difference is that you have multiple instances of objects or elements in those sets. And so what happens is that first you embed each element, and then you aggregate each element, and then you have fully connected layers. For the bag, where you have multiple instances of the same elements, you do a weighted aggregation instead. Date and age tree features are first divided in their components. For instance, for date, it's divided in month, day, year, day of the month, day of the year, hour, and minute. And then each single component is embedded, and then they are aggregated, and something similar happens to H3 too. Finally, vector features are just taken as they are and passed through fully connected layers. So now we've seen how you can have several different data types in your model, but when you have more than one, you have to have a mechanism to combine them. And the combiner does exactly that. There's several combiners in Ludwig. The most simple is the concat combiner that takes several inputs and just concatenates their vectors and passes them through fully connected layers. There's other combiners that are more sophisticated that you can check out in the Ludwig documentation. Then, depending on the type of task that you care about, you can have different data types for the decoding and for the output. For instance, for numerical features, what you have is that you train a model that projects into a one dimension, and then you can use mean squared error for computing the loss and updating your weights. And you have control over the loss and all the parameters. If you want to do binary classification instead, you can use a binary output feature. It's identical to the numerical feature. The only difference is that you have an additional sigmoid at the end, and the loss that you use is cross entropy, in this case, binary cross entropy. For category features, this could be used for doing multi-class classification, and you have a projection to the number of the classes and a softmax, and you train this with softmax cross entropy. And you have a lot of parameters here for the loss to play around. For set features, those are useful for doing multi-label classification, and is the same principle of the multi-class classification, but just you do a sigmoid instead of a softmax, because more than one class can happen at the same time, and so you use sigmoid cross entropy in this case as a loss. For the vector feature, you're predicting entire vectors, and you can use either mean squared loss or cross entropy if you want to apply a softmax layer before the final prediction. Sequence features are a little bit more complicated. There's 2 types of decoders in this case. There's a generator and a tagger. The way they work is the following. So the tagger assumes that the input is a sequence and provides one class for each element of the input sequence. And this is useful, for instance, for tagging text. You have a piece of text that says Blade Runner is something, and you want to extract the movies from this text, and you can tag movie to Blade Runner and other class to any other word. Instead, when you have two sequences that are of different length, you want to generate the the target sequence in an autoregressive way by computing the outputs one at a time and then backfeeding the output that you produce at the previous time step at the next time step, and keep on generating until a specific token is generated, that like end of sequence token or something like that. This is useful, for instance, for machine translation. There's also a bunch of training parameters that you can change within the model definition in Ludwig. There's the batch size, the number of epochs, which optimizer to use, if you want to use weight decay, learning rate decay, and so on and so on. You have full control over the training. And you also have full control over the preprocessing, because there's you can specify all the parameters of the preprocessing, like for instance, how you want to split your data, or for each type of feature, different parameters. Like for text, you can define how long the maximum length of the text, either in characters or in words, or how many words you want to keep in your vocabulary. Currently, for text preprocessing, there's a bunch of languages that are supported thanks to importing Spacey, which provides this tokenization. So let's see some examples. The first example is the model that we have already shown, where you have news and class, and it's a text classification model. On the right, you can see the model definition. This is all you have to write in Ludwig in order to obtain a model that does that. But if you want to have an image classification model instead, the only difference is that in this case, the name of the input feature will be image path, because that's the name of the column, and the type will be image instead of text. And the encoder here we specified, for instance, that we want a stack CNN. If you want to do a speaker verification system, here you have two input features that are of type audio, and one output feature that is of type binary. And the idea is that you want to return true if those two samples are from the same person, or false otherwise. And this is all the code that you have to write. It's not really code, it's just simple configuration. This is a model that we are using at Uber. It's like the simplification of that model, really, but the basic idea is the same. You have expected time of delivery of a specific order from a specific restaurant, and you have, again, the restaurant treated as a category, the order treated as a bag, and then hour and minute treated as numbers. And what you want to predict is the expected time of delivery in minutes of how long it's going to take to deliver this order. Another possible example of a model you can do with Ludwig is a sequence-to-sequence chit-chat dialog model, where you have the first user that produces, that utters something, and another user, maybe a system, that answers that utterance. And you just have one input feature and output feature, both of type text, and the decoder in this case uses a generator. And here I'm also showing how you can use, for instance, an RNN encoder and specify the cell type of that RNN, and also the attention mechanism if you want. On the converse, you also have sequence tagging, where you have pieces of sequences, and you want to tag each element of the sequence with a specific class. In this case, N stands for noun, and P stands for person, and D stands for date. And so you see that there's a one-on-one mapping between the elements on the utterance and the elements of the tag. And all you have to do is you have to specify in your output feature type sequence and the coder type tagger. So if you want to use Ludwig, it's really easy to install. Just pip install Ludwig, and this is all you need to know about the programmatic API. You just import Ludwig model class from ludwig.api, and you create an instance by providing a model definition. On that instance, you can call train to train the model on some new data, and you can call predict to use it for predicting on some unseen data. And you can also load pre-trained models by ludwig model.load. And if you want to serve the model as a REST API, all you have to do is call Ludwig serve and the path to the model that you trained. You also have a bunch of visualizations available to you. I will not get into the details, but this is like a subset of what you have. There's more than 20, but this is, a subset of them. The first one is a comparison of the model performance. The second one is a calibration plot. The one in the middle at the bottom is a comparison of the predictions. So you have a full set of options here to use. And in version 0.3, which is going to be released probably in a month, there's a bunch of new features. Not all of them are fully implemented, but some of them are already there. So for instance, you will be able to do hyperparameter optimization. On the left, you have your Ludwig model configuration, and on the right, you can specify an hyperopt section where you specify which metric you want to optimize, which parameters and their range, and which strategy to use to optimize, if a random random strategy grid, a grid strategy or a Bayesian strategy, and how to execute it, if in parallel or in a serial way or on fiber, which means on a cluster. If you want to train in a distributed way, all you have to do is to add -- use Horovod to the Ludwig command and run it through run Horovod, which Horovod is like a project also released by Uber that allows for training in a distributed setting. We recently added the Neuropod export. Neuropod is this new thing that Uber is providing for serving models in production. And basically, you take your Ludwig model and export it as a Neuropod, and then you can serve it super easily everywhere. You can also do k-fold cross-validation in version 0.3, just specify the number of folds. And you can, the base code of Ludwig is being ported to TensorFlow 2, so now you can add your custom encoders, for instance, as TensorFlow 2 layers. Super simple. You will also be able to use all the transformers from the Eigenphase transformer library. And you will also be able to have a preprocessing pipeline plugged with the data type that you care about. And if you want to do it in memory or from HDFS or from file, you have all these options. Finally, there's also integration with weights and biases for monitoring your models. And there's also another one with Comet ML that was already implemented in the previous version. This custom model interface is something that I haven't added yet, but it will allow you to just specify your model in terms of an init function, a call function, and a training step. And you will be able to train any model that you want, any custom model. So these are the next steps that I'm going to do with this TensorFlow 2 porting. Will enable like more features, more pre-trained models, and also will add some more pluggable data pipelines. So these are a bunch of links that you can check. Ludwig.ai, there's documentation, and there's the repository, which is going to be moved soon to be part of the Linux Foundation. There's also a couple blog posts, some videos, and a white paper. And you can check all of these things. And also I wanted to thank all the key contributors to this project, like Yaroslav, Sai, Jim, Ivailo, John, Doug, Patrick, Carlo, Chris, and Boris. So now what I'm going to tell you about is one specific project, COTA, that we developed using Ludwig. Let me open that up. All right. So this project is like a project where we used Ludwig, but in general deep learning techniques for improving customer support at Uber. And is a project done in collaboration with Waishu Zhang and Yichao Wang from the Applied Machine Learning team. So there's two versions of COTA. One, the version that uses classic NLP and machine learning models, and the second one with deep learning models. What I'm going to tell you about is the second one with deep learning models. And there's a blog post and a follow-up and a KDD paper. So if you want to know more, there's plenty of information online. So first of all, what is the challenge that we're facing? So there's every week, Uber receives millions of tickets from users for riders, drivers, and eaters. And there's thousands of different types of users issues that they may face. And so we want to make our customer support representatives as fast as possible and as accurate as possible. The process works like this. There's a user that selects from the UI a flow node and writes a message about what issue they are facing. A contact ticket is created and is provided to the customer support representative, CSR. And what they do is first they select the contact type from a list that they have, from actually a hierarchy that they have at their disposal. They look up some information and what are the policies for this kind of tickets, and they select an action. And after selecting an action, they write an answer using some templates. And in the end, a response is provided to the user, and this could be a loop, like the user can answer back. This is the interface that the customer support representatives see every day on the left. And as you can see, there's a selection between the different types. There's more than 1,000 types structured in a hierarchy, about 20 different actions, and actually not 1,000, more than 6,000 different reply templates that they can choose from. And so these problems can be pretty difficult and time-consuming for them. we will not touch on the action part because it's relatively easy. We will touch on the classification and on the reply template. So let's skip the V1 part. Let's talk about the V2. So what we are using for creating the deep learning architecture is Ludwig. So this is a slide that depicts an earlier version of Ludwig, but then we released it as open source. So we increased the number of features that were supported. And we compared different text encoding models. These were the ones that were available in Ludwig at the time, the character CNN, word CNN, character and word RNN, and character and word CNN. In the end, what we decided to use is not the most performant one, which was the character CNN RNN, but we used the word CNN because, as you can see, on the validation accuracy, there was not a huge gap in performance between the two, but at training time and also prediction time, there was a huge gap there. And so we selected to use the word CNN because it was the most practical option at our disposal. And one thing that we added is that instead of, because the contact types are organized in a hierarchy, instead of predicting directly the contact type, we predicted the path in the tree from the root node to the contact type leaf node that we care about. And we do that with a sequence generator, as I explained before in Ludwig. The final architecture that we use contains a text feature, and it's the convolutional layers are used for encoding it, and a bunch of categorical, numerical, and binary features. All the outputs of these encoders are concatenated in a big vector that is passed through fully connected layers with dropout. And then we have two output features, one for the type and one for the reply. And we also feed the output of the type as input to the reply, because obviously if you know which contact type you're trying to solve, that informs you on which reply you want to use for replying to the user. This is a comparison with and without using that dependency. The absolute performance does not change a lot. It improves just a little bit, but if you look at the combined accuracy, which means the number of data points on which both predictions are correct, it increases a lot, which means that the prediction from the two different heads of the model are more, let's say, coherent with each other. And so we also compared with the previous version, which was based on random forests and manual feature engineering. And we improved substantially on all the metrics that we cared about, from 10 to 20% relative improvement. We conducted an A/B test to check if the system that we were providing to the customer support representative was actually useful to them. And what we discovered was that using COTA, both V1 and V2, you can be 20 to 30%. Actually, the V2, so the deep learning version, is 20 to 30% more accurate than the version 1 on the A/B test, and reduces the handling time by a 15% overall. And the customer satisfaction improves. It does not improve in a significant way, even if it's not a substantial improvement. But our goal was not to improve the customer satisfaction. We wanted to make sure that by increasing the speed and the accuracy of the customer support, we were not impacting the customer satisfaction, because it will be easy to be super fast in answering, but answering the wrong thing, right? And we did an additional analysis where we had the moving threshold on the output confidence probability of the model, so that we can swipe this threshold. And as you can see, the left side, when the probability is low, it's more likely the model is going to produce something wrong in red, while when the threshold is higher, the probability of the model producing something correct in green is much higher. And so we displayed this as a plot of the data coverage that the threshold imposes. So I only answer to the tickets where I am more confident than a certain amount, and the accuracy. And as you can see, the accuracy grows linearly. And you can draw that also in 2D, because we have both a threshold on the contact type and a threshold on the reply. And if you do that, and you just reproject to 1D, you can see that basically we can answer 10% of the tickets and 95% accuracy, and 20% of the tickets and 90% accuracy. And so for those subset of tickets, we can actually entirely automate the process. But because the remaining of the tickets can be safety related or security related, we always want to have a human in the loop for providing the answers. Yeah, so these are some conclusions of this work. We use using NLP and MLP, you can make customer support faster and more accurate, and save the company millions of dollars. Actually, using deep learning models can provide a performance boost up to 30% in our specific with our specific data, and you can reduce the ticket handling time without impacting customer support satisfaction if you use this intelligent suggestion system for your customer support representatives. And that's about it. Now I think we have some time for questions, I believe, right?
Yes, we are in perfect time. So I don't see any question in the chat. So if are there any question, now is the moment. You can write them in the chat, or now you can also turn on your webcam and unmute your micro and ask directly to Piero. Also in Italian, if you want, if you are more comfortable, then we can translate it in English for the broader audience, so feel free. Now it's the moment. I had a question, but Piero, you already answered me. It was related to the integration with Neuropod, but you already thought that is in the roadmap, probably also in the next release. So.
No, actually, it's already there. So it's not in the release, but it's already in the master. So if you go there, it's already working.
Oh, perfect.
Because actually, I mean, they announced it yesterday or like 2 days ago or something like that, but I was already using it inside the company. So we already had that working, really.
It's good. Yeah. Perfect. For the serving part, it's perfect. So it's very good. I don't know if someone have any question. Please be brave. It's your moment.
Yeah, you can, Michael. Okay, answer.
Yeah. So first of all, amazing job. It's truly impressive. Since we are, this tool seems to be very easy to use also, as you mentioned, for a novice. Have you experienced in Uber some people maybe from the business side that wanted to maybe explore using, like, creating some machine learning product, sometimes as the business go, and how easy was for them if you experience these kind of things?
Yeah, so actually, guys, let me stop the sharing so that we can see, hopefully you can also see my face. Okay, yeah, so Ludwig is much simpler to use than, for instance, TensorFlow or PyTorch, just because of the reason that using those kind of tools, you have to write the models on your own. In Ludwig, you just have to declare what you want in terms of the inputs and outputs. You don't have to specify how the inputs and outputs are mapped one to each other. You don't have to specify anything, right? So it enables less sophisticated user, and sophisticated I mean in terms of machine learning knowledge and technical knowledge to train deep learning models. So when the way I've seen that, the way I've seen Ludwig being used inside Uber was from not directly from business users, because in Uber, basically each single business unit is composed of a bunch of different people with different backgrounds, with both engineering backgrounds and data science background, together with people with more business and product background. So it's almost never the case within Uber that there's a team that's only made of business people, only made of product people. And so I haven't seen them directly using it, but there have been many product teams that had no deep learning expertise or no data scientist among them that were able to use Ludwig for solving their business needs. Some examples are, for instance, classifications of queries that are coming to the Uber website. Now it's done with Ludwig, for instance, or also we had this project with for prediction of the time of delivery for for Uber Eats, but also another project for Uber Freight, so that basically you were predicting how long the cargo delivery would take, and a bunch of other tasks done by business units that didn't have a lot of data scientists among them, but they were still able to use deep learning models, and that was kind of, a positive outcome, I would say, for Ludwig, I believe.
Yes, I think also because all the default value for the parameter that are automatically set for a non-expert data scientist are really useful to keep on track very, very, very fast. Because
exactly. So, I mean, obviously, if you want to squeeze the performance out of your models, you may want either to do the hyperparameter optimization because I recently added it, or you want to tune those parameters. And for doing that, well, you may kind of want to know a little bit what those parameters are and what they do, right? But you can get 80% there without doing anything, and then you can decide how much time and effort you want to invest to squeeze an additional 20%, right? It's your choice. You have the options to do it or not. But for doing like a prototype, you can get a prototype running in no time, really.
And that's also really good because in a lot of companies, this can help to do the first proof of concept in order to see if there is a feasible solution for the problem. And then you can bring into the team the data scientist to improve and get the improvement in the performance. But you can very quickly find out if the problem is solvable in a good way with a first run without involving all the data scientists.
Exactly. It's like it's perfect for those kind of use cases. And also, it's true both in many companies. It's true also in Uber. It's like a chicken and egg problem, right? We have a business task, right? But we don't want to invest millions and millions to solve it with machine learning solution without knowing that there's a hope that machine learning solution will actually deliver some value, right?
Yeah.
And so this allows you to quickly prototype, do a really small investment, figure out something, and then decide if to do the real investment later on, right?
Yeah, that's really important. Also because for what I see in a lot of company, maybe Uber is different, but I think at a different scale the problem is the same. The number of data scientists is limited respect to the number of problems that they can try to manage. So having a tool that allows also the product team to do a triage of all the possible interesting use case to see what is feasible and what is not feasible. It's a good screening that allows to save some time to the data scientist in order to focus only on really important problem that already made a business case.
Yeah, totally agree. I think there's another question that we see in the chat.
Yes. Sorry.
Okay, so is if you can do ensembles in Ludwig. No, you cannot do ensembles directly in Ludwig, but that is, I would say, an outer loop around Ludwig, and so you could easily train a bunch of Ludwig models using different architectures and just ensembling their outputs easily. I don't think that that's any difficult, really. It's just a for loop. That's all you have to write in order to do that. Another question. Would you recommend as hardware and network cloud Docker setup?
Actually, hello. My name is Tian Jovchev. As you're reading my question, I can just ask it directly. So my question was, what is the recommended network cloud-based, maybe Docker solution to set up a service based on Ludwig? Or what will be the bottleneck? Where is the border between the need to switch to a different setup to run, let's say, a web service?
Thank you for your question. So I think that there's the short answer is it depends, and the longer answer is if you care mostly about the productionization and so the prediction side of things after the model is trained and when you want to query the model really, it's a set of answers. For training is a different set of answers. The reason is, depending on the model, models can be like bigger or smaller, and you can do batching or not. So for some models where batching makes more sense, you have an substantial advantage by using GPUs, for instance. For models where you cannot batch that much, the advantage of using GPU is smaller. So that depends on your choice of model. And that's for the hardware side. In terms of like Docker and cloud providers, Ludwig is really agnostic with respect to that. The command that I showed you, the one that allows you to serve models, Ludwig serve, and the model path, creates a Starlet REST API. Starlet is like a super fast Python, the fastest probably Python option for serving REST APIs. And so once you serve that REST API, you can do it from like anywhere really, as long as you can like run a process. So I don't have like a specific suggestion for you. I would say Ludwig comes with also a Docker image that you can use as a base for your serving, but you can spawn that image in any service provider really. There's no. It's more a matter of for you of cost than anything else, and how easy is it for you, and how used you are to a specific cloud vendor, rather than a technical issue. It's more a matter of preference.
Thank you. Thank you very much.
Let's see if there's other questions. It doesn't seem like.
I have another question while we are waiting for if there are any other questions from the audience. Do you plan also to introduce in Ludwig something to automatize some boilerplate part related to feature engineering? I think, for example, augmentation or stuff like that, or is something that is from your point of view outside of the framework?
So Ludwig at the moment doesn't do feature augmentation, but already contains the code for doing preprocessing from raw data to tensors. The way you could see it is that you could see it in two ways, right? On one hand, you could see it as, okay, I can do my feature augmentation and any manipulation of the data set outside Ludwig, and then I provide to Ludwig the output of that process, right? And that's, in that case, I wouldn't have to do anything within Ludwig. But there's some optimization that you can do to the process if you do it within Ludwig. And so I'm considering adding more feature engineering options to Ludwig. Although at the moment, the preprocessing pipeline is configurable, so you have many parameters, but it's kind of fixed. One thing that I want to introduce, either in the 0.3 version or maybe in the 0.4 version, I will decide where to put it, is the possibility for you to provide like a pluggable way to provide your own pre-processing pipeline. And in that case, the advantage would be that you will have full freedom to like write the code for your pre-processing pipeline and plug it in. But that's at the expense of the fact that then you need to know what you're writing, right? So I want to strike a balance between easy of use, and I want to provide both really, like custom pipelines that optionally people can provide, and more advanced pipelines that people can use without having to actually implement them. And so, for instance, for images, that's something you can relatively easily do, to add a flag in the preprocessing that says do augmentation by like rotating the images and flipping the images or like distorting them somehow, right? Things like that. That I will want to add. I would say I will put it in the backlog because there's, as you've seen, there's a bunch of people that are helping out with this project, and I really thank them. But it's also true that the vast majority of the tasks I've been doing myself. So, I have to be mindful of my time and how to prioritize the different things that I want to put in the project.
Yes, sure. I understand. Now, because you have talked about the hyperparameter optimization, and I think that also in feature engineer, there is a part that is an art, of course, and require all the knowledge of an expert data scientist, but there is also some boilerplate part, like, for example, image augmentation or how to manage imbalanced data set. There is some strategy that are basically have a nice default that can be applied. I see.
No, I totally agree, and I think that the thing there is that the art of the data scientist is more in the choice rather than implementation. Implementation is in the most cases trivial, and so if you provide all the implementations or a subset of like reasonable implementations for the different options, and then you let the user choose which one is the the best one for the specific case that they are facing, I think that that's a good value, right? Because you're allowing them to do their job, but at the same time, you are avoiding them to reinvent the wheel every single time, re-implementing every single time. Mapping to log space of numerical values or things like that, right? You don't want to have them re-implement those things. That actually, this touches on the reason why I created this toolkit to begin with. The reason I created it is that I'm super lazy, and I don't want to do, if I have to do something and don't want to do it, I can do it 2 times, but the third time that I do it, I automate it because I get bored really easily of doing repetitive tasks. And so that was my main reason. I wanted to, for instance, implement a training loop, a really good training loop once and for all, and never have to re-implement it ever in my life. And that's the reason why I actually did Ludwig, because now I don't have to re-implement the training loop. And whenever I change the training loop to include a new feature, all the models that I previously trained, I can retrain them with this new feature super easily, right?
Yes, but that's also good for a team standpoint, because they can share the standard that is extensible. But the problem in some team, especially when they are not so much mature, is also that the approach is I have my code, I have my library, I reuse my snippet of code, so everybody do the same thing, a little bit different, instead of having a tool like that.
Yeah, but there's a big problem with that. The big problem is that you create technical debt. Those kind of one-off solutions that work in one specific case, and then you can basically never reuse. Maybe you can reuse some lines of code, but you cannot reuse the project in its entirety. And that's a problem, because you spend a lot of money and a lot of time and a lot of effort in building things that you cannot reuse, and that's.
Sometimes even yourself, you cannot reuse the code that you have.
Exactly. You don't want to be in that position, right? A tool like Ludwig actually allows for the opposite of that.
But in fact, I think that for the expert user is very good, because automatize a lot of boilerplate stuff, and so allow to iterate more fast. And also for the learner is a very good tool. Actually, I'm not a data scientist. I'm more a data engineer that have studied data science, and I start to study data science with FastIE and the learning course of Jeremy Howard. And the approach is very similar. Start to create your algorithm using a library that implement all the default from out of the box. And then as soon as you start to have a more complex problem, or you want to optimize more, or when you have more knowledge, you can open the toolbox and start to customize different parameter and do a better model. So this approach is, I think that is also very, very good for the person that start to learn data science, because I have not to understand everything before to start to write a line of code, but can directly start to create the model and then go deep as soon as they learn more stuff. So very good.
Yeah. Makes a lot of sense.
Okay, I think that there are not any more questions, so we are 10 minutes late, but we have started 5 minutes late, so we are perfectly on time. I think that we can close. Thank you very much, Piero, for spending an hour with us. The presentation was super useful and interesting. The recording will be available in the next days. I don't know if we can share also the presentation with all the
is already on my personal website. I can give you the link so that
everybody... Okay, perfect. If you share the link with me, then I publish when I send the mail with the link to the recording. I will share also the link to the presentation. So okay, thank you everybody, and see you next time. Bye bye.
Bye.